a relentless battle rages within the depths of stellar existence. Gravity relentlessly pulls cosmic bodies inward, while their internal heat fights to expand them outward. For most of their lives, these two titanic forces remain locked in a delicate yet stable equilibrium. Yet for a star like our Sun, this harmonious balance shatters at the twilight of its life. During this phase, it briefly swells to enormous size, blazing with extraordinary brightness, only to cast off its outer layers, leaving behind nothing but a gravitationally compressed core. This remnant fades away, emitting, metaphorically speaking, a mournful groan and lament. Of course, this is the groan and lament of a nuclear-powered fireball, barely under control, weighing an octillion tons. But stars far more massive than the Sun do not submit so quietly to their inevitable fate. Their demise is marked by a cataclysmic explosion of truly staggering proportions. Deep within a stellar core, unimaginable pressures and temperatures enable atoms to fuse, releasing colossal amounts of energy and forging heavier elements. Hydrogen fuses into helium, helium into carbon, and the heavier the element, the more extreme the conditions of heat and pressure required to create it. Low-mass stars like our Sun stop at carbon. Once this element accumulates in their core, the star's fate is sealed. However, if a star exceeds the Sun's mass by more than 8 times, its core can reach temperatures above 500 million degrees Celsius. Under such conditions, carbon itself begins to fuse. This process unfolds through several sequential stages, ultimately transforming carbon into neon, magnesium, and a small amount of sodium. What follows mirrors what we've seen in the Sun's core over time. The fusion of one element yields a heavier one, which accumulates until the core compresses and heats enough to ignite its own fusion. Thus, carbon fusion produces neon, magnesium, and sodium, which gradually build up. As the core heats to around 1 billion degrees Celsius, neon begins to fuse, creating more magnesium and some oxygen. These newly formed elements accumulate, causing the core to contract and heat further, reaching about 1.5 billion degrees Celsius. At this point, oxygen fuses into silicon. Silicon, in turn, accumulates until temperatures soar to roughly 2 to 3 billion degrees, enabling silicon itself to fuse. Silicon fusion yields, among other elements, iron, and this marks a serious, even critical turning point. Once silicon fusion begins, the star effectively becomes a ticking time bomb. But before we delve deeper into that, let's step back and consider what happens to the star's outer layers. What would we see if we observed it from afar? Because the star started with substantial mass, it spent its hydrogen fusing phase as a brilliant blue main sequence star, exceptionally luminous and visible across vast cosmic distances. Like the Sun, however, this massive star evolves when hydrogen fusion ends, its core contracts, helium fusion ignites, and the star swells. But instead of becoming a red giant, it unleashes colossal energy and transforms into a red supergiant. These stars are astonishingly large. Some exceed 1 billion kilometers in diameter, and they shine with extraordinary brilliance. Betelgeuse in Orion, for example, is a red supergiant and one of the brightest stars in the night sky, despite lying over 600 light-years away. From that distance, our Sun would require a powerful telescope to be seen at all. And that's not all. VY Canis Majoris, the largest known star, spans 2 billion kilometers, so immense that such behemoths are classified as hypergiants. As the core cycles through successive fusion stages, the outer layers respond by alternately contracting and expanding. Thus, a red supergiant may shrink and become a blue supergiant. Rigel in Orion is a prime example, a blue supergiant radiating 100,000 times more energy than our Sun. Returning to the core, we find it has developed an onion-like layered structure. Iron accumulates at the center, surrounded by shells of fusing silicon, then oxygen, neon, and carbon-helium, and finally hydrogen. One might assume more massive stars live longer due to greater fuel reserves, but their cores are far hotter, fusing elements at a dramatically accelerated rate and depleting fuel much faster. A Sun-like star can fuse hydrogen steadily for over 10 billion years. A star twice the Sun's mass exhausts its hydrogen in just 2 billion years. And a star 8 times more massive burns through its hydrogen in about 100 million years. Each subsequent fusion stage proceeds faster than the last. In an extreme case, a star 20 times the Sun's mass, helium fusion lasts about 1 million years, carbon fusion only 1,000 years, neon fusion burns out in a single year, oxygen lasts mere months, and silicon fusion consumes all its fuel in 1 day. Yes, 1 single day. The overwhelming majority of a star's life is spent fusing hydrogen. Everything else happens in the blink of an eye. From this point, events unfold with astonishing speed. Silicon fusion produces a range of elements, most critically, iron. This inert iron, like its predecessors, accumulates in the star's center, forming a core. With each new stage, the iron core compresses and heats, a natural progression. But here, a fundamental difference emerges. All previous fusion reactions released energy, which became heat, providing the outward pressure that supported the star's immense mass against gravitational collapse. Iron behaves differently. Fusing iron doesn't release energy, it consumes it. Instead of feeding the star, it drains its vital energy supply, accelerating core contraction and heating. The situation worsens. Under extreme heat and pressure, the iron core begins absorbing surrounding electrons, particles that had helped stabilize the core. Thus, a double blow strikes simultaneously. 2 critical supports vanish almost at once. Silicon to iron fusion proceeds with terrifying speed, completing in mere fractions of a second. Deprived of support, the core doesn't just shrink, it collapses. Gravity becomes so intense that the star's outer layers plummet inward at nearly the speed of light. This catastrophic implosion crushes the core from hundreds of kilometers down to just tens of kilometers in a few thousandths of a second. The star's fate is sealed. Chaos is inevitable. At this stage, 2 outcomes are possible. If the star's mass is below about 20 solar masses, the collapse halts when the core reaches roughly 20 kilometers across, forming a neutron star, a subject we'll explore in a future episode. But if the star exceeds that threshold, no known force in the universe can stop the collapse. The core continues shrinking until gravity becomes so powerful that not even light can escape. A black hole is born. Another topic for a future installment. For now, let's examine what happens when the core collapses and then suddenly stops. Whether it becomes a neutron star or a black hole, the remnant is now incredibly small, yet possesses immense gravity. It violently pulls in the overlying material, which plummets inward, compressing and heating intensely. Two key events occur simultaneously in the core. First, as matter falls inward, a powerful shockwave, generated by the core's collapse, propagates outward and collides with the infalling material. The explosion's energy is so great that it dramatically slows the infall. Second, complex quantum processes in the core produce a colossal flood of subatomic particles called neutrinos. The total energy carried by these neutrinos is almost incomprehensible. In mere fractions of a second, they transport 100 times more energy than the sun will emit in its entire lifetime, a truly staggering amount. Neutrinos are famously elusive, rarely interacting with ordinary matter. A single neutrino could pass through trillions of kilometers of lead without noticing it. But during core collapse, so many neutrinos are produced, and the infalling matter is so dense that a vast number are absorbed. This immense neutrino wave slams into the incoming material like a high-speed train hitting a block of hot butter. The infall halts, reverses, and surges outward. The star explodes, literally tearing itself apart. This event is known as a supernova, one of the most magnificent and terrifying phenomena in the universe. An entire star destroys itself, and the expanding gas blasts outward at up to 10% the speed of light. The energy released is so immense, it can be seen from the far side of the observable universe, outshining all the other stars in its galaxy combined. The expanding debris, called a supernova remnant, takes on extraordinary shapes. The most famous example is the Crab Nebula, the remains of a star whose explosion was recorded in 1054. Its intricate filaments form as the ejecta plow into surrounding gas and dust. As remnants expand and age, they thin out. Some develop glowing edges as they collide with interstellar material. Others form complex filamentary networks. A common question arises: are any stars close enough to harm us if they explode? The short answer is no. Despite a supernova's colossal power, space is vast. To cause real harm, a supernova would need to occur within about 100 light-years of Earth. The nearest candidate is Spica in Virgo, but it lies well beyond that safe distance. Moreover, its mass sits near the lower limit required for a supernova, so it may never explode at all. Betelgeuse, on the other hand, will certainly explode someday, but its distance ensures our safety. Humanity is well shielded from this particular threat. It's also worth noting another type of supernova involving white dwarfs, which we'll cover in an episode on binary stars. Fortunately, we appear safe from those as well, so there's no need for alarm. Yet as fearsome as supernovae are, they are vitally important. Supernovae can wreak immense destruction, but they are also essential to our existence. During the explosion, gas is heated to extreme temperatures and compressed so violently that fusion occurs in what astronomers call explosive nucleosynthesis, literally, the creation of heavy elements through explosion. This process forges new elements in quantities far exceeding Earth's mass. Calcium, phosphorus, nickel, and more iron, all forged in the inferno of a supernova and scattered across the cosmos. Over thousands of years or more, this material mixes with interstellar gas and dust clouds. Sometimes, these clouds naturally form new stars. Other times, a supernova's shockwave triggers cloud collapse, sparking star formation. In either case, the heavy elements forged in the supernova become part of the next generation of stars and planets. Supernovae are the primary mechanism by which most heavy elements were created and distributed throughout the universe. The calcium in your bones, the iron in your blood, and the phosphorus in your DNA all were forged in the heart of a dying star's majestic death. That star exploded over 5 billion years ago, but its remnants still live on in your body. To summarize, massive stars fuse heavier elements in their cores than low-mass stars, progressing all the way to iron. Iron drains energy from the core, triggering collapse. A shockwave, powered by an immense flood of neutrinos, blasts through the star's outer layers, causing a supernova explosion. This explosion creates even more heavy elements and scatters them across space. And fortunately, no nearby supernova currently threatens Earth. This episode was written by Phil Plait, edited by Blake DiPestino, and reviewed by Dr. Michelle Thaller. It was directed by Nicholas Jenkins and edited by Nicole Sweeney. Sound design by Michael Aranda, and, as always, our graphics team is Thought Cafe.